and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today, I'm continuing day 12 of the Advent of Code. This is garden groups, and I actually found it a really interesting puzzle. Yesterday's video, I completed part 11, started part 12, got a whole bunch of code for grouping contiguous regions of letters together. So let's say in this block, this whole group of E's here would be formed into one vector from multiple vectors. Unfortunately, although all the test cases passed, the full input puzzle did not pass, or rather it took a very, very long time. So I'm going to quickly scan through the code, see what's going on, and then we're going to try and fix it. We're going to try and do a new way of doing it. Now, overnight, I did think of a better way to read things out of the puzzle. So first I want to check that what I'm doing is actually optimizing the right thing, which is making the contiguous groups faster. Because if they don't need to be faster, there's no point writing the optimization. So first thing I'm going to do is insert some code to print out when it's doing each letter so that we can see how fast it is. Okay, so let's take a quick look through the code because there's not a whole lot here. There's a from string function which will read out all of the characters into a 2D vector. Actually, it does it into a hash map of car to vector of points. Then it does this group contiguous. That takes one vector of points and turns it into a vector of points, where each inner vector is a contiguous group. So this is the group contiguous function. It is a little bit more complicated than I would like. But it essentially goes through all the points, checks it against all the other points and tries to group them together. And if it manages to add a point to a group, it then has to check all the groups it's already found to see if those groups are now touching one another, and if they are to form those into one contiguous group. So that's the code as it is. Let's insert those print statements and check that that's actually the slow part, as I suspect. And if it is, then I have a good idea of how to almost entirely skip it by doing a different method of reading out the puzzle. Let's give it a go. Here we are. In for each, we've already got a block here. So I think all I need to do here is print line, grouping, letter, and then give it the plant type. So now if I cargo run this, and you can see it's grouping letter P and it's grouping it very slowly. S's, A's, Q's. So yeah, nearly all of the runtime of the program is spent grouping regions into contiguous regions. So I am satisfied that that is the slow part of the program. I was almost certain, very nearly certain that that was the case. So what I'm going to do now is change it to a different way of reading. Instead of reading in a vector of points for each letter type, I'm going to go over the whole 2D array, and for each one, I'm going to take the starting letter and try and flood fill to find all the same letter in a contiguous region. I could do it recursively. I'm going to try using an iterative method using a stack to store which points haven't been explored yet. So you might be able to tell I've been mulling this over in between videos. So let's give this a go. We're going to start with what we've got. We've already got this for loop. So what I would like to have is a stack, which is a vector. For each vector, actually, yeah, that's fine. And then we're going to have a let mute explored is a hash set new. Because I want to, as each point is explored, I want to figure out, I want to keep track of whether it's been explored so that in future iterations, it doesn't repeatedly try and find it again. Okay. So we've already got the row and column. We're already iterating over everything. So what we're going to do now is if explore.contains the current value, which will be and point row and col. Continue. If we're in this loop and we've already grouped the point we're checking with another region, we don't need to look at it. Continue on. Okay. I'm going to get rid of this because I don't want to get confused by it. So we've got this check. So if we get to this point, we've got a row index and a column index that has not yet been explored. At which point we want to put it on the stack. It would be the same point. So actually what I'm going to do is let point is point. Then I'll reference point, and then down here I will push the point. Now, while stack dot length greater than 0, we're going to keep checking different points on the stack and then pushing it onto the stack again. So stack is mutable. I'm hoping that checking this length doesn't count as an immutable borrow, but we'll have to see on that one. Okay, while stack.length is greater than 0, we want to take the point that is on the stack. I'm just going to reuse point because we don't really need it anymore. So I'm going to pop. I am going to unwrap because we've just checked that the length is non-zero here. Maybe I'll turn it into an expect. Stack is unexpectedly empty. Okay. With that point, I want to explore in every direction. And I also want to check if do you know, I think it might be easier to read out the puzzle into a 2D vector and then use the grid. So yes, that's what I'm going to do. At which point I'm just going to do it at the top here. Okay, so let mute grid is vector. I'm going to specify the type so it's readable in code. I think it is useful at this point. It's a vector of plant types, which makes them cars. Now I'm going to use this iteration. I'll close it off. And for each one, I am just going to... In fact, I can turn this into a full iterator. So puzzle.lines.map. Each line becomes l.map or iter, nope, cars. l.cars dot collect, I think. And then we collect it. Now, we don't actually need this grid to be mutable. We can straight up just read the puzzle in. It's a puzzle, not puzzles. Yeah, and that is the grid read in. So now I'm going to change this to grid.iter.enumerate, and I'll change this to sorry, this will be row still, but it'll be iter. We're iterating over a vector of characters. We're not taking a character iterator. Right. So now this is a U size. We can convert this to an I32 and this also to an I32. I want to have a bounds check. So let in bounds, and I could define this as an external function, but I'm going to take advantage of the closure's ability to read local variables if they're present. So I'm going to take a point which is a reference to a point. And I will return that the grid dot, well, it will be that point.0 is greater than 0, greater than or equal to 0, and point.1 greater than or equal to 0, and grid dot, wait, so that would be point.0 less than grid dot length, and point.1 is less than grid 0 dot length. Now let's check that. So 0 is the row index, the length is the number of rows, so that's right, I think. This will need to be as an I32, and this will also need to be as an I32. That is happier. Okay, great. We've got our complete explored list and our stack list. We can now do... our stack is a push, but we don't need to explore the same thing twice. I wonder if we should make this a hash set as well. If we can pop off a hash set. Can we pop off a hash set? Doesn't look like it. Stack dot. I just want to get anything. Yeah, I don't think you can. Okay, so we're going to keep that as a vector. I can just do a contains instead of letting the hash set deduplicate for me. Okay, so we've got our point. If explored contains the point, then we continue. Now we're going to push the point. We are going to explored.insert that point. Now we need to check in all directions of point. In fact, I want to create a current region is a hash set new. Then current region becomes a hash set new at the end here. So I'll explain what that is an attempt to do once I've finished this logic. Okay, so this is upset because it doesn't know what type current region is, so bear with me on that. So we're going to check in all directions of point. So for let all points is direction, horizon vert, and we're going to map it to take a direction and do point.add d dot. D is a direction. D is an and point. Is it? It should be a direction enum, no? Yeah, the direction enums. I don't understand. I'm going to code it like I'm expecting it to be coded. Okay, so I'm actually going to filter on this as well. I can take out the ones that are... So for point P, it needs to not be in bounds. And if that's the case, then we want to push it onto the stack. So I might even just be able to directly insert here. So stack.extend all points. Okay, now we have to call into iter, apparently. That's fine. It's producing a new vector every time anyway. Let's format this so it's easier to read. Okay, so for each one, we're checking if it's within bounds. If it is within bounds, we're like putting it onto the stack to explore for the next iteration. While that's all good, we should also check that it's not in explored already. So I'm going to add a new filter clause for that, .filter. And I think that's more likely to happen, so I'm going to move it higher up. I don't know if that makes a difference. Now I could do one filter with like 2 or 3 ands in, but considering Rust compiles it down to the same code anyway, I don't feel the need to do that. So explore.contains p. So if it's not been explored, remove it, or if it has been explored, remove it basically. Wait, I think I have the logic wrong here. 1 second. I think this filter needs to be in bounds. Only keep the points that are in bounds. Now there's one really important thing that I've not done yet, which is to check the plant type. So let's check plant type, and we're going to look it up. Actually, the plant type should always be the same, so we don't need to look it up here. We want to look it up down here. So we're going to check it's in bounds, we're going to check it's not been explored, and we're going to check that for a given point, that our grid p.0, p.1 is equal to plant type as usize. Dereference the borrow, and that should work. So for each one, we want to insert it into the current region. Length comparison to 0 while not is empty. Yeah, let's do that. Great. Then this says you seem to be trying to pop elements from a vec in a root in a loop. Oh, okay. I didn't know you could do that. So that's very cool, Clippy. Thank you. While let point is stack.pop, and then sum. So then I don't need this. That's cool. That's very cool. All right. We don't need this map, I don't think. At this point, okay, not at this point. At this point, just before we reset current region. So in our algorithm, we take a point, we put it onto the stack, then we repeatedly take the item from the stack and check the neighbor points that are within bounds, haven't been explored, and are the same plant type, and we put those on the stack. And we keep doing that until we found all of the things that are in the plant type and have added them to current region. At that point, we can create... oh, did I just delete the map? At that point, we can add it to our regions. Now, another point here that you might have figured out is that we don't need to store the regions at this point. We could just calculate the perimeter and so on. And that would be more efficient, but I'm not trying to make the most efficient thing possible. I'm just trying to solve the puzzle, and I think it makes more sense, at least to me, to save it and calculate it at a later step. So I'm going to take the regions. Regions will be a hash map new, and then it's a car to vector, a vector of points, which is what I expect. So now I want to insert it in here. So my regions is going to get the entry for the plant type, and or default, which should produce a vector. dot extend with current region. Is that happy? Let mute regions. I need to dereference this. And then type annotations are needed. Type annotations are not needed. Because I plug it in here, it should know what regions is. I'll explicitly state it. Even auto completes it. Look at that. All right. Okay, this is why. So current region should be, yeah, a hash set. Actually, it doesn't need to be. It could just be a vector. There's no benefit from making a hash set. So let's make it a vector and then push it. We're going to push point. Then we're going to iterate. Why is that unhappy? Because we found a reference to a point. What does it think the default is? Or insert with vector. Is that okay? And then extend by oh yeah, and this we then need to clear it. Clear? Clear. Type mismatch. It expected a vector of points and it found a point. Current region's not a point. It's a vector. Is it expecting a point? I don't understand what's going on here. I'm going to run a test and see what it says. So current region is a vec of points. So it doesn't want an iterator, it just wants the vector. Is that better? No. I don't know why it thinks current region is a point. It's really odd. I don't understand what the error message is saying. So we've just inserted a vector, right? So we should at this point be able to extend on the vector. What does it say if I autocomplete here? What does it think it can do? It can join, can as pointer, can it push? It can push. Extends a collection with the contents of an iterator. Right. Current region dot iter. That's an iterator. Extend it. Okay, I'm pretty confused about what's going wrong there. But I think that once I've resolved that line of code, it should work. Is it append rather than extend? It thinks I can push. a vector into a vector. Is that what the problem is? Oh, that's right. I am trying to push a vector. Okay, so that's Rust's type system saving me from making a mistake. I was trying to push all of the points within current region, and if I had done that, I would have combined all the current regions together into one big region. So good thing that it wasn't able to do that. Now, can I push a copy of it? Wait, does clear return all the items? No. Okay. Or insert. Yeah, it should be or default. That's fine. I'm okay with that. I mainly just wanted to make sure it was a vector type. Now we've got more things here. P is already a reference. Redundant closure, replace with and inbounds. Oh yeah, that's cool. So I can just do and inbounds. And then here, group contiguous is no longer necessary, hopefully. Let's do a test and see what comes out. Oh, 3 failed. That is unfortunate. The length is 5, but the index is ridiculous. That's really odd. They're all panicking at the same point, which is 48. Let's take a look. For some reason it's getting p.0 is an enormous number. So clearly I've done something wrong here. Let's debug test1.txt. I'm just going to comment these out so I can see what's going on. Let mute regions, and we're going to debug this. Here we go. So within bounds is there. Our grid is A000. I mean, that's already fairly odd. B000. Let's just print out this grid and make sure it looks right. It might just be looking weird because I'm viewing it in the debugger. And just do a quick cargo test, see what that grid looks like. Okay. No, the grid's okay. The grid's fine. Let's our inbounds. Maybe the inbounds is wrong. Maybe it's doing a -1, which is overflowing it. So then point.0 greater or equals 0, right? Is it this? Is it that? So we only keep it if explored contains P. We only keep it if the plant type is the same, and we only keep it if it's in bounds. And we're doing the index lookup before we're doing the inbounds check. So really, this should be here. Okay. Now that is still not correct, but it's not correct in a way where I'm indexing by an insane number. All right. All right, let's have a look at what regions is when we get out here. Okay, let's have a look. So let's take a look at A. A. Not 0, not 1, not 2, not 3. Check. Let's check B. B is 1, 0, 2, 0, 2, 1, 1, 1, 1, 1. Okay, so that's wrong. That's why we had current region as a hash set, because we didn't want to add the same point to it multiple times. So I broke it by trying to add it on. So what I can do here is current region dot to vec, maybe iter dot to vec select into a vector of points. Although it should just be able to take the iterator. Let's just try and take the iterator. Oh no, it does need to be a vector of points. It can't be built, but we can do an into. Yes. Now it is happier, and then this needs to be an insert, not a push. Apparently it's borrowed after move. Where is it? If I do a cargo test here, it might give me another, it might give me all the, oh, clone. I just need to clone it. That's fine. So here you go, Rust's helpful compiler suggestions. I figured I might need to clone it. Let's format this and run it again. Okay, we've got a test pass. So I should now be able to, whoops, reinstate the other tests. And I think I can probably remove the print lines, right? Those are the only print lines. Good. Let's run the test again. Okay, very quickly passed. Let's cargo run. And it took a moment, but it was much, much faster. So yeah, I'm happy with that. And I didn't use a recursive function, which I'm happy about. Let's remove this whole group contiguous function, which is no longer necessary. And check the answer. So here we are. I can remove this tab now. I can submit the answer, and it's the right answer. Too many times I finally got the answer, plugged it in, and it says no. Okay, so now I'm going to read out the part 2 of day 12. Feel free to skip ahead, the chapters are set up. So, part 2. Fortunately, the elves are trying to order so much fence that they qualify for a bulk discount. Under the bulk discount, instead of using the perimeter to calculate the price, you need to use the number of sides each region has. Each straight section of fence counts as a side, regardless of how long it is. Consider this example again. The region containing type A plants has 4 sides, as does each of the regions containing plants of type B, D, and E. However, the more complex region containing the plants of type C has 8 sides. Using the new method of calculating the per region price by multiplying the region's area by its number of sides, regions A through E have prices 16, 32, 4, and 12 respectively, for a total price of 80. The second example above, full of type X and O plants, would have a total price of 436. Here's a map that includes an E-shaped region full of type E plants. The E-shaped region has an area of 17 and 12 sides for a price of 204. Including the 2 regions full of type X plants, this map has a total price of 236. This map has a total price of 368. It includes 2 regions full of type B plants, each with 4 sides, and a single region full of type A plants, with 4 sides on the outside and 8 more sides on the inside, a total of 12 sides. Be especially careful when counting the fence around regions like the one full of type A plants. In particular, each section of fence has an inside and an outside, so the fence does not connect across the middle of the region, where the 2 B regions touch diagonally. The elves would have used the Mobius Fencing Company instead, but their contract terms are too one-sided. Oh, that is a terrible pun. The larger example from before now has the following updated prices. If that confused you, take a look at what a Mobius strip is. It's a one-sided surface, so it's just a loop turned on itself, so it only has one side infinitely long. So the contract terms being too one-sided, there you go. The larger example from before now has the following updated prices. I'm going to skip reading this. I think you can read it on the screen. Adding these together produces its new total price of 1,206, What is the new total price of fencing all regions on your map? I have no idea how I'm going to calculate that fence. Let's take a moment to think about it. Okay, so one thought is, instead of taking 2 away for a wall, a fence that both letters, that's skipping ahead a bit. So my method for working out the perimeter was to assume that each plant had all 4 walls, and then checking if it had a neighboring plant, and if it did, remove the wall. But of course you have to remove 2 walls because there's 1 wall from the left plant and 1 wall from the right plant that need to be removed. So my initial thought is, if you find a neighboring plant, not only do you remove the 2 walls between them, but you also remove 1 wall and 1 wall from the other plant because it's your wall extended along, right? So I think that works if they're all in a straight line. So you take the 4 A's all in a row. You can take 16, take the farthest left A, you go across 1, it's another A. So you remove 4 walls. So we're now down to 12. Next A, another 4 walls gone, 8. The next A, another 4 walls gone, 4. The last A doesn't have any other neighboring A's because they've all been checked already. So that would give us a wall count of 4. So that works for 4s. Now for B's, I think it's a bit different. I haven't checked it through, but what I think happens is, actually, it doesn't work because the C's would have exactly the same logic, but they've got a direction change which increases the number to 8. So I may have to count the number of straight lines. If I can reduce it to the number of straight lines, that might give me the answer. So it's, if it's 1 straight line, then it's 2 squared, which is 4. The C's have 2 straight lines that are touching, effectively, which would mean 2 cubed, which is 8. The B's have 2 lines, but that's 4, so no, that doesn't work. I'm not entirely sure how to do this. It might have to get a lot more algorithmic. So maybe we go over all the points and we figure out if there is a wall there that we can't go past. That doesn't account for direction of movement. Okay, we put our pin on A. We try to move in all directions. We can go right, so there's no wall there. So far we're on try up, there's a wall, try left, there's a wall, try down, there's a wall, so that's 3 walls. Go right, no wall. We try right, there's no wall, we try right, there's no wall, and now there's 3 walls again. And the wall, 2 of the walls need to be removed because they're still on the same straight. I'm sure there's an easy way to do this. I'm struggling to think of what it is. It's interesting that the numbers we've got are all multiples of 2 on A through E. So I wonder if we can just double it. So, you know, it's the number of changes in direction multiplied by 2. I mean, D still needs 4 walls, so that doesn't work. Maybe for each plant I can count its neighbors. For A, it would be 1 neighbor, 2 neighbors, 2 neighbors, 1 neighbor. For B, it's 2 neighbors, 2 neighbors, 2 neighbors, 2 neighbors. So that immediately doesn't work. It gives a different result from the A's. The B's and the A's have the same number of fences. So whatever algorithm I've got has to give the same result for a row of 4 and a square of 4. I'm struggling to think of a neat mathematical way. I mean, multiply the number by 4 and then remove 1 every time you find a neighbor is very neat, but it doesn't work in this case. I wonder if it's possible to go around the outside. That doesn't give me the internal number, but let's say that my point is 0, 0. I'm going to start with 2 walls because I'm in the top left. And my point is 0, 0. Now I try to go right, and I find a number. So I don't add a wall. I go right again. I'd probably try and go up and left. So you try and go left, up, right, down, maybe. This is the point where I would get pen and paper out. Try and figure out how to group these together. So if I've got 4 in a row, then I want to group 4 around. You'll have to excuse the terrible drawing. I'm drawing with my finger on a touch screen. Okay, and then we've got this. And we also want to be able to draw this. So I really liked the perimeter equation algorithm. And I'm still trying to think if there's an easy way to do it that's just like it. Okay, so we know that 1 on the edge has 3 walls. But the tricky part is that if we start on the left and we have 3 walls, we can go right because that doesn't have a wall. That's okay. So we don't add any walls, we just extend them along. At this point, we need to check whether we can go down, which we can't, or right, which we can, up, which we can't. We can only go right, so we move along another one. And again, same logic. Now we can't go anywhere. So we could just terminate and at that point add 1. So it's 3 walls, add 1 to close it, makes 4. Let's say we take our B's. B, B, B. Now we know we've got 2 neighbors, so we can only have 2 walls. We're able to go up and we're able to go right. So for each of those, we're going to explore. We're able to go down, able to go right. I think I said up there. So if we go right, that's okay because it's the initial direction. So we don't add anything. Then once we get to this B, we need to check if we can go down, but we can't go anywhere else. So because we were traveling right, and now we've had to change direction, now we need to add a wall and change direction. So it's basically like we're iterating in a direction. So for our 0th point count walls, it's 4 minus number of neighbors. But how do we finish this up? We've changed direction to down. Maybe we only ever go right and down, but we always start from the up and left direction. So like we take our vector and we sort it, and then we only ever go like that. Does that work? So from our first point, we need to run the algorithm twice from this B, one to go right and one to go down. We get to this B, we're traveling right. There's no way to go right. Add a wall, change direction, because we're able to go down. At this point, we can't go down, so we add a wall. And we're done, because we can't go right or down. So we've got one wall from traveling right, one wall from traveling down. This one. We've got one wall. Well, actually, these are from my starting point of counting neighbors. So we've got two walls, up and left. We've added one wall from traveling right. Now we're traveling down. We're traveling down, and we're able to go right. So we go down. We're not able to go down anymore. We add a wall. Now we have to go right. But because we've already explored that point where we keep and explored, please don't make fun of my writing. Ooh, seems to have given up anyway. Ooh, that's even worse with the trackpad. Okay. So that's possibly an algorithm. We take the upper left point or the uppermost point followed by the leftmost point, and then we can only travel right and down. And then we have to repeatedly do that for each leftmost point. Oh, this is getting complicated. Don't save. We're going to do more regions. Let's take a look. So let's do our C's now. Our C's go like this. We have a C, C, a C, a C. We start at the top. We've got our three walls because there's only one way, and that's to go down. So that's our starting three. We are traveling in the down direction. Now this next point, we can't travel down anymore. We have to travel right. So we're going to switch to a right direction and add a wall. So we're now on 4. This direction we're traveling right. We can't travel right anymore. So we put a wall. So that's 5. And then this direction we can't travel right anymore. We've got to go down. And we can't go down anymore. So we add a wall. Which gives a final result of 6 because we haven't accounted for this wall or this wall. So that algorithm does not work. Okay. Day 12 is causing me some serious trouble, huh? I wonder if we can literally draw the fence. So if our point A is at 0, 0, then we're going to let's do that 2, 3, 4. So we're at 0, 0. Can we draw the fence up? No, because there's no point at this point. That doesn't exist. Can we go left? No, there's no point here, so we can't do it. Can we go down? No, there's a plant there, so we go right. So now we're here. Same logic, can't do it. Same logic, can't do it. Now, can we draw the fence? How do we do the corner? So I think I need some time to think this one through. Come up with some different ideas on how to do it. So I'm going to stop the video here. I'll be back tomorrow or maybe sooner if I come up with something. I would like to try and solve this myself. I'd like to think of a good solution. I'm pretty satisfied that my grouping up solution works better from yesterday to today, and I would like to do the same thing for part 2 of the puzzle. If I can't think of something, having thought of it, then tomorrow's video will be looking up more suggestions on the net, or just looking up a solution from another person's advent of code, and just figuring out that key point of how to calculate the number of sides, continuous sides. So with that, as I said, I'll stop the video. I'll see you tomorrow, or maybe sooner if I come up with something. Thank you for watching.